All right. In this lecture, we will see a general version of Cauchy's theorem, which is another weapon that we'll have at our disposal in our quest for classifying uh, all finite groups. Now, um, in a previous lecture, perhaps you recall that uh, we've said that we've established Cauchy's theorem for abelian groups, and precisely we have proved that if G is an abelian group and P is a prime number dividing the order of G, then G has at least one element of order P. Now, we will generalize this result to the class of non-abelian finite groups. So, in other words, the result that we have proved for abelian groups doesn't just hold for abelian groups. It generalizes to all finite groups, abelian or non-abelian. So, however, before we get going, we'll need a little bit of preliminary work. This being a pretty powerful result, we don't expect it to get it for free. All right, so let's get started. Let us consider some examples. Consider the finite group Z4 consisting of elements 0, 1, 2, and 3, which we endow with addition mod 4. So the operation here is addition mod 4. Now, let's look at all of the orders of elements in this group. The order of 0 is 1, right? Because 1 is the smallest number, such that when you add 0 to itself, you get 0, which is the identity. The order of 1 is 4, because if you take 1 plus 1, that will be 2. Plus 1, that's 3. Plus 1, that's 4, but 4 mod 4 is going to be 0. So the order of 1 is indeed 4. What about 2? 2 plus 2 is 4, and 4 mod 4 is going to be 0. So the order of 2 is 0. And again, one can check very quickly that the order of 3 is 4. And this is actually due to the fact that 3 and 1 are inverses of each other with respect to addition mod 4. And so they have to have the same order because they're inverses of each other. Now, notice that the prime decomposition of 4 is 2 times 2. And so 2 is the smallest prime number dividing 4. And clearly, you can see here that there is one element of order 2. Now, we are not surprised here because Z4 is abelian. We already know from the proof of Cauchy's theorem for abelian groups that this result is going to hold. But it's still nice to revisit things that we know. Now, let's consider the following group of order 10. This is, in fact, a non-commutative group. Now, if you write down the prime decomposition of 10, that'll be 2 times 5, right? And 2 and 5, okay, the only prime numbers dividing 10. Let's just look at 5 right now. And consider the elements R. If we take R power 5, what is that? That'll be R cubed R. But if you take R and R cubed together, what we get, if you take R cubed times R, you get F RF times R, and then by associativity, this is essentially FR times FR. And let's look at what is FR times FR. That's the identity. Yeah. So 5R has for order 5. That's what I mean. All right, let's consider another non-abelian group of order 12. And let's suppose that you're given the following multiplication table. Let's consider the elements 0, 1, 3. So we have here 0, 1, 3, 0, 1, 3. So if we take 0, 1, 3 time itself, we get the element 0, 3, 1, whatever that is. Now, if we take 0, 1, 3 cube, then that will be essentially 0, 3, 1 times 0, 1, 3. So what is 0, 3, 1? It's here, time 0, 1, 3, and we get the identity element, which is denoted by simply just the empty parenthesis. So this again shows that 0, 1, 3 has order 3. Why is this relevant? Well, the prime decomposition of 12 is 3 times 4, right? And 3, so 3 is clearly a prime number dividing 12. And we were able to find an element inside the group which has order 3. Oops, I meant here is 3, equal to 3. Now, so this can't be a coincidence, right? So we seem to be verifying these results over and over. Now let us try to understand what is happening here. So what we really want to prove is the following. We would like to prove that if G is a finite group of order n, and if a prime number p divides n, then there must exist a non-identity element x such that x time itself, p time, will be the identity. So in other words, the equation yp equal to the identity has a solution which is not the identity. This is what we want to prove. Okay, now we need some preliminary results. We need some tools before we can establish our result. Let S be a finite set. Recall that AS is in fact the collection of all functions mapping S2 into itself such that F is a bijection. So it's the set of all bijective functions on S. Now we'll define a relation on S as follows. We'll say that two elements X and Y are related to each other if and only if there exists an integer K such that X is equal to F composed with itself K time applied to Y. So what does this notation mean here? If K happen to be positive, then we mean that we are composing F with itself K times. If K is negative, we are composing F inverse with itself, absolute value of K times. If K is the identity, then if K is 0, then Fk is just the identity map. That's what this notation Fk means. Now, I will leave it to you to verify that this is actually an equivalence relation. So you just have to show that it satisfies all three axioms required to be an equivalence relation. Now, suppose we have accepted the fact that the relation X is related to Y if and only if there exists some integer K such that X is equal to Fk of Y is an equivalence relation. Then an equivalence class, which will denote by bracket of X, will then of course consist of all points in the set such that all point Y in the set such that X is related to Y. And we will for this particular type of equivalence class, we will call such an equivalence class an orbit of X. So by orbit of X, we mean the equivalence class of X. And again, clearly we've seen in a previous lesson that any equivalence class will give a partition of the sets, right? So this is then telling us that if you write an equivalence class, then it will look like this. You have to have the identity elements. You have to have the element itself, and then you'll have I'm sorry, here is X already here, and then you have f of X, and you'll have f of X, and so on. You'll have the inverse of f applied to X, and so on. All right. So in other words, you start with an X, you get f of X, you get f of X, f inverse of X, f inverse of X, and it keeps going in this fashion in all directions. Okay. All right. So that's what an orbit of X is. Let's consider some examples. Let S be the set with 4 elements, 1, 2, 3, 4. Let's consider the map F, which takes 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And the inverse of F will, of course, take 1 to 4, 2 to 1, 3 to 2, and 4 to 3. Simply just reverse the arrows here. Now, let's see what's happened for the orbit of 2. Well, if you take 2, 2 goes to 3, right? Since 3 is f of 2. But then if you compute f of 2, well, that will be f of 3. But f of 3 is 4. And if you compute f of 2, this will be f of 4, but f of 4 is 1. But then again, if you apply f to 1, you get 2. So this is telling us that the orbit of 2 is actually the entire set S. So that means that for this equivalence class, for this equivalence relation, we only have exactly one orbit. Every element in the set is in the same orbit. Now, let us consider another equivalence relationship given to us by a different function. In this example here, we have the same sets, but f is actually fixing 1 and 3, and then it swaps 2 and 4. And you can verify that f is in fact equal to its inverse. So to compute the orbit of any element, we just need to focus on f. So let's see what happened to 2. If you take f of 2, we get 4, right? But if you compute f of 2, then we get f of 4, but f of 4 is 2. And then you keep circling back. So 2 goes to 4, 4 goes to 2, 2 goes to 4, and so on. So these orbits, an orbit of 2 consists only of 2 elements. However, if you compute f of 1, you get 1. Then it doesn't matter if you compute f of 1, you're still going to get f of 1, which is 1. So for any k, which is an integer, f of k of 1 is always 1. So 1 has, the orbit of 1 is a singleton containing itself. And a similar observation holds for 3. So we have in this equivalence relation, we have 3 orbits, 2 of them is a 2 orbit is a set containing is an orbit containing 2 elements, and the other 2 orbits are just singletons. All right. Let's consider now a set which is not infinite, which is not finite. So instead an infinite set, and let AR be the set of all bijection on this set, which we choose here to be the set of all real numbers. Now we'll choose a specific function here, which is a bijection. Is the function which maps every real number to its double. That clearly is a bijection. Now one can compute that f of x is actually 2 square of x, and you can check in fact that fn of x is 2 power n of x. Okay, now to compute the inverse of this function, so you do what you did in pre-calculus. You set y to be equal to 2x, and then you solve this for x, so that gives you that x is equal to actually y over 2. So this tells you that the inverse of this function is actually x over 2. So if you try to compute f inverse of x, we write this as 2 power negative 1x, then this will be f inverse of 2 inverse of x, which is 2 power negative 2 of x. And you can prove by induction that for every natural number n, it's actually just 2 power negative n and then x. So this tells us that the orbit of x consists of all numbers of the type 2 power n x, where n is an integer. Okay, now given a function f in AS, the set of all bijection on S, we'll say that the order of f is the smallest positive integers for which fn is the identity map of S, if there is any. Otherwise we'll say that the order of f is infinity. So if k is the smallest positive integer such that fk is the identity map, then we'll say that the order of f is k. Otherwise, if such a number does not exist, we'll say that the order of f is indeed infinity. Okay, all right, so our first result states the following: if f is a bijection on S and is of order p, where p is a prime number, then the orbit of any element of S under f has one or p many elements. Okay, so let S be an element of the set. If it happens that f of S is S, then you can verify that for every integer k, we'll get that fk of S is going to always be S, and that tells you that the orbit of x is just a singleton containing S. Okay, so this is not an interesting orbit, but in any case we get that it is possible for the orbit to just consist of one element. Now suppose that f of S is not S, and let us consider the following sequence. We take S, we take f of S, we take f of S, and we keep going in this fashion all the way till fp minus 1 of S. And we aim to show that these sets here has precisely p minus 1 element. So what does that mean? Suppose otherwise, then there must exist two integers k and j, where k is strictly less than j, and they're all in between 0 and p minus 1, such that somehow fk of S is equal to j of s. So the idea is, if this result was not true, then you should be able to find two elements in this set which are equal to each other, but they come from different functions, and call j the larger exponent essentially. Then by applying fk inverse f negative k to each side of the equation, we'll get that s is fj minus k of s. But then keep in mind that j is greater than k, so that means that j minus k will be a strictly positive number. Okay, so we can write s again as fj minus k of s, and letting m be j minus k, m is positive and m has to be less than p minus 1 by construction, and on top of that fm of s is s. So s is fixed under the action of fm. But since f is of order p, it must be the case that fp of s is s, right? That's what it means, because fp is the identity map, right? Since fp is the identity map, it has to fix s. Now, since p does not divide m, right, then that means that p and m are relatively prime, and we know what that means is that you can find two integers a and b such that the integral linear combination ap plus bm is equal to 1. Now, so if we rewrite fs as again f power 1 of s, then this gives us fap plus bm of s. Okay, but this is just fap of bm of s by the assumption that fm of s is s. This will be fap of s, and by the fact that fp of s is s, this will be s. All right, so far we proved then that f of s must be equal to s, but this violates the assumption that f of s is not s, and that gives us the desired contradiction. So we have proved the lemma. Now we are actually ready now to prove Cauchy's theorem. To recall the statement, the theorem says the following: p is a prime number and p divides the order of g. If this is the case, then you can find an element x in the group G such that the order of x is actually p. All right. So let's suppose that p is equal to 2. This really tells us that G is of even order. Okay. And now let S be the set of all elements of the type. So this contains all order pairs of the type x inverse, where x is running through all elements of G, but then we prevent x from being the identity element. If S only consists of order pairs of the type xy such that y is never x, then you should be able to rewrite to essentially enumerate all elements of G such that by pairing every element with its inverse, you have x1 inverse, x2 inverse, and so on all the way till xr inverse, and then of course you'll have the identity here. But then if you rewrite this and you do the counting, then this is telling us that the order of G is essentially 2r plus 1, because you have even many elements here, and then you have the identity, right? So, but this will imply that the order of G is odd, contradicting the fact that the order of G is even. Okay, so that gives us so this is telling us that there must exist at least one element of the type XX, right, in S. But the fact that this is an element in S implies that X must be its inverse. And then if you multiply this equation on the left by X, you get X squared is E. So this tells you that X is a non-trivial element, it's a non-identity element, and its order is 2. And this confirms Cauchy's theorem for all groups which have even order. Alright, let's suppose we consider the case where P is the prime number 3 and 3 divides the order of G. And we'll consider S to be the set of all triples of the type XYZ, such that XYZ is in G and X times Y times Z is the identity element in E. Now, since XYZ is E, solving this for Z implies that Z has to be equal to X Y inverse times E, which is just XY inverse, which is Y inverse X inverse. Alright, so that means that if we write out the element in S, it must be of the type XY, and then we'll have here Y inverse X inverse. And the only thing that is important in enumerating the elements of S are just X and Y. So if we want to count the elements in this set, we only need to consider the parameter X and the parameter Y, because the third parameter depends on these two. There are, if we let N be the order of G, then there are n many ways of choosing X, right? There are n many ways of choosing X. There are n many ways of choosing Y. Then this tells us that the cardinality, of S is essentially n squared, which is the order of G squared. That's how many elements we have in the set G. Now we will also consider a function f which is mapping S to S such that is send f of x, y, z to z, y, x. So this is essentially just sort of rotating around the coordinates of x, y, z, if you will say. So z move here, and then this will move there, and then this one will move here, right? So sorry, I want to have z, x, and then y. Okay. All right. So essentially, it's sort of shifting things around. It will move z to the first, x goes to the second, and y goes to the third. And I will ask you to pause the video here and, as an exercise, show that f is a bijection. Okay. Now, the assumption that P is equal to 3 and 3 divides the order of G, that means that we can find two distinct elements of X in G and call such element X and Y. So this is telling us that at least G has at least 3 many elements. So if you disregard the identity, you should be at least able to find two distinct elements. Call them X and Y. Now set z to be xy inverse. Then what will happen is that f of xyz, right, will be f of x y xy inverse. And if you if you apply the map f, then you get here xy inverse x and then y. And I claim that this cannot be equal to its input. Why? Because if it was equal to its input, then it must be the case that these two elements here will be the same, but we have assumed that they're not the same. So this function does not take xy inverse to itself. It can't. That tells you that f is not the identity map, because there's at least one element in the set S which does not go to itself. So f is not the identity map. Now, since f has order 3, you can check that if you're permuting, if you're just shifting the component around just once, then since you have 3 many components, if you shift 3 times, you get back to where you started. Now, by the preceding lemma, we know that any orbit under the action of f will have 1 or 3 elements, since 3 is prime. Now, since S is partitioned by its orbit, the cardinality of S can be computed as follows. So if we define that 2 elements are equivalent if and only if they are in the same orbit, then this will partition S into orbits induced by the map F. But we already seen that we can only have orbits consisting of 1 element or orbits consisting of 3 elements. Okay, so let n be the number of orbits with precisely 1 element, and let m be the number of orbits with exactly 3 elements. Then you can then rewrite, because the orbit partition S as S, the cardinality of S is n times 1, right, plus 3 times m, that's n plus 3m. And we know that we have this many elements. Now, solving for n gives us that n must then be the order of g squared minus 3m. Now, keep in mind that the order of g is a multiple of 3, right? So we can rewrite this as, let's say, 3l squared minus 3m, and that will be 9l squared minus 3m, and we can factor 3 out, so we get 3l squared minus m. So this tells us that 3 has to divide n, where n is the number of orbits with 1 element. So since 3 divide the order of g, it follows that n is a multiple of 3. In other words, there are at least 3 distinct 1 element orbits, and one of them is given by the triple EEE. So that means that we can find x, y, and z not equal to the triple EEE, such that the orbit of x, y, z is a set consisting of 1 element. Okay, so now let's look at the elements in the equivalence class of such element. So in the equivalence class of x, y, z, we will of course have x, y, z, and if we apply f of x, y, z, we get z x, y. And then if we apply again, what do we get? We get y zx. But then we say that all of these are in this this is a one orbit element. So all of these must be actually equal to each other. So that tells us that x must be equal to z, which must be equal to y, by just looking at the first entry in these triples. So this tells you that if this is a one orbit, if this set has only, if the equivalence class of xyz only has one element, then xyz must be x, 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 and x is not the identity element. All right. So now, we saw that xyz is x, 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 but because this element is in S, then if we multiply x times x, that's x cubed, and that has to be in E. And x is not the identity element. So we have just found one non-identity element of order 3. And now, the reason why this example, this case is super important is because the general proof, when P is a prime order and not 3, essentially mimic these steps. So instead of rehashing the same techniques, I'm going to leave it to you to verify the steps, that these steps essentially can be rehashed for the general case. Similar arguments work for the cases where P is greater than 3, and the details are left as a reading assignment. So I'll refer you for your textbook for that. We will now explore some direct consequences of Cauchy's theorem. The first one says the following. Suppose that G is a group of order PQ. P is prime and P is greater than Q. Then this result says that G has a unique subgroup N such that the order of N is actually equal to P, and in fact N is also normal in G. All right. So the mere fact that P is prime and P is greater than Q gives us all of these results here. So let's see. So by virtue of Cauchy's theorem, we know that there exists an element X of order P, and let N be the group generated by X here. So we let N be the group generated by X. Correct this typo here. Then we first aim to prove that N is unique, not A. So suppose otherwise that there exists a subgroup M which is distinct from N, which is of order P. Okay. Since P is prime, then M is necessarily cyclic as well. We argue next that the set NM and the set Nm consists of all elements of the type N, M, such that N is in big N and little m is in big M. So we want to prove that this set has exactly P squared distinct elements. In arguing that, first it is clear that by construction Nm has at most P squared many elements, because there are P many elements in N, P many elements in M. So the largest possible number of elements that Nm can have is P squared. We just want to check here that it's not possible to take different products which will give us the same elements. That's the only thing that we need to check here. So suppose by contradiction that there exists two distinct pairs, N and M. So we have here that N and M and U and V are distinct pair. So here N and U are in N, and little m and V are in M. And somehow when you take N times M, we get So somehow when you take n times m, we get u times v. Okay. Suppose by contradiction such an element exists. So if we rewrite this, then this will tell us that u inverse of n must then be v m inverse. Thus, notice that u, we said that u is in n, right? And what about n? N is in big N. Now v is in m, and m is also in m. So that tells you that u inverse n is in n, and v m inverse is in m. And the fact that u inverse n is equal to v m inverse implies that both of these elements, u inverse n and v m inverse, they're the same actually, belong to n intersect m. They belong to the overlap of this group. But the intersection of two subgroups is always a group itself. You can check this at home. Now, so n intersect m is a subgroup of n, and m and its order must then divide the prime number p. So that means that the order of n intersect m is either going to be 1 or it's going to be p. Okay. Now, if the order of n intersect m is p, then this tells us that n must be equal to m, which is n intersects m, right? Because if the overlap is everything, then both elements must be the same, and this will contradict our assumption. So that means that the order of n intersect m is 1. So, but that tells you then that u inverse of n must be v m inverse, and that is in n intersect m, so that must be the identity. But if that's the case, then that tells you that u must be n and v must be m, which then implies that the pair nm must be the pair uv. But this contradicts the fact that we have stated here that these are distinct pairs. Okay, so thus the pairs and then are not distinct. I mean here that the pair here are distinct, and this shows that this gives us the desired contradiction, telling us that m has exactly p squared distinct elements. Okay. Now, but this will imply that p square, since so the point here is that nm is a subset of G. But it has order p square. It has p square many elements. So p square has to be less or equal to pq. Dividing by p on each side will imply that p is less or equal to q. However, this will contradict the assumptions that p is strictly larger than q. Okay, thus n must be unique. All right. Now let us prove the normality of n. So let G be an element of the set of the group G. Then the conjugate of n is a subgroup of G. Now consider the map phi, which sends G and G inverse to n as follows. Phi of G and G inverse is n. I claim that this map is a bijection, so this is a homework for you to make sure that you're paying attention. Show that phi is indeed a bijection. That will imply then, because it's a bijection, that the order of G and G inverse is equal to the order of n, which is P. Can you see what is happening already? They have the same order, but we already seen that there's only one subgroup of order P. So that means that G n, the conjugate, any conjugate of n must be equal to n, but that's precisely what it means for n to be normal. Is normal in G. All right. So any subgroup of order P is unique and is also normal. Very good. So next, our next result says that suppose that the order of G is equal to PQ, where P and Q are both prime, and P is greater than Q, and Q does not divide P minus 1. Then we want to show that G is cyclic. Okay? All right. Let's get going. So according to Cauchy's theorem, G has an element X of order P, and Y must also have an element of order Q because both P and Q are prime. Now, since the group generated by X is normal, there must exist an integer K such that K is sitting in between 0 and P, not equal to 0, not equal to P. And by cyclicity of the group generated by X, Y inverse must be of the type X power K. So here we're applying both normality and cyclicity to get this for some integer K. Okay, now, okay, so now, so if you compute y square x y inverse, what is that? This is going to be y x y inverse, which is going to be y x k y inverse. Okay, now notice that yx is essentially xky. So if you rewrite this as yx, and then we'll have x here, y inverse, we can, just looking at yx and looking at this equation, this will turn into xky, and then you have y minus 1. And so they're here k minus 1, many elements left here. But each time you try to swap this, you have to use this formula here, right? So if you use that formula each time, you'll get xk, and then you get xk, and then you get to the next again, and then you swap, you apply this formula, you do that k minus 1 many times, you'll get a total of xk times k, which is xk square. Okay, all right. So then generally for any j which is an integer, you can prove by for which is an integer, you can prove by induction. Let's say that j is positive. Let's say, for example, that j is positive here. So you can prove by induction that yj x y inverse of j is going to be xk power j. Okay, now if we rewrite x as exe, then because yq is e, y is of order q, so, and then our previous observation gives us that we get x q power k, and but this will means that e must be x qk x inverse, and this will be x qk minus 1 must be equal to e. Now this implies that p divides qk minus 1, okay, because the order of x is p. Okay, but this really means that the fact that qk divides p divides qk minus 1 means that we can rewrite qk minus 1 as pl, which then implies that qk is equal to pl plus 1, but this will mean that qk will be 1 mod p. Now regarding k as an element of the multiplicative group 1, 2, all the way till p minus 1, which is endowed with multiplication modulo p, it follows that the order of k must divide q. Okay? Again, let me repeat. We regard k as an element of the multiplicative group 1 through p minus 1. So the fact that x, let's go back here, we saw that, okay, k q is equal to 1 mod p tells us that the order of k must divide q. Okay, well, since q is prime, the order of k must either be 1 or q, and the order of q must divide p minus 1. Yes, because it's an element of this multiplicative group which has order p minus 1, and since q does not divide p minus 1, the order of q cannot be equal, the order of k cannot be equal to q. Okay, so this forces k to be 1, and as a result we get that y x y inverse must be equal to x. Okay, and now, so that this tells us then that yx must be xy. Okay, now let z be the element xy. By assumption, the order of z must be either 1, pq, or pq, right? Okay, because z divides, the order of z must divide the order of pq. But since x and y generate disjoint subgroup of G, the first three options are out of the question. So I'm saying that it's not possible that the order of z, it's not possible for the order of z to be either 1, p, and q. I want you to pause the video and really try to digest this for yourself. Try to see why this can't be the case. I claim that the reason why this substantiating this is because x and y generate disjoint subgroups of G. Now this shows that Z has order PQ, and consequently G must be a cyclic group generated by Z. Right? Because we have found an element of order PQ, but the group has order PQ. Alright, now let's G be a finite group of order 4. Let's take the prime decomposition of 4, 2 times 2. Notice that if P admits an element of order 4, then G is a cyclic subgroup of order 4, right? So that's that. Now, let's suppose that G is a finite group of order 4, and suppose that G admits no element of order 4. Then G must admit two distinct elements of order 2, right? That's Lagrange theorem, essentially, because every element of the group must have an element which divides the order of the group. That gives you a possibility of 2 and 4, but 4 is out of the question by assumption, so all possible orders must be 2. And in that case, we get a group which is called the Klein group. I want you to pause the video here and to try to make sense out of the Cayley diagram of this group. So essentially here we have classified all groups of order 4. Such a group is either isomorphic to Z4 or it's isomorphic to Z2 cross Z2. Now let G be a finite group of order 15. The prime decomposition of 15 is 3 and 5, right? Well, now 3 and 5 are prime numbers, and then 5 is greater than 3, and also 3 does not divide 5 minus 1, which is 4. Then our previous results applies right away. So this tells us right away that G is cyclic. Automatically, we can say, so any group of order 15 is necessarily cyclic, even though 15 is not prime. Okay.